At exactly T-minus 30 seconds before liftoff, the automated flight sequence takes complete and total control of the launch. June 4, 1996, in Kourou, Guyana. Standing on the pad is the Ariane 5, the flagship heavy-lift vehicle of the European Space Agency. The weather conditions at the site are within acceptable margins. The physical hardware has passed every pre-flight inspection. Nearly $500 million of equipment and payload are locked in and ready. At T0, the main engine and solid boosters ignite flawlessly. The massive vehicle clears the launch tower. For the first 36 seconds of the flight, the rocket performs exactly as designed. Every physical telemetry sensor reports nominal behavior as it accelerates into the sky. Then, exactly 37 seconds after liftoff, the vehicle issues an unprompted command. The nozzles on the main engine and solid boosters swivel to their extreme positions, forcing the rocket to veer sharply off its flight path. The massive aerodynamic forces of this turn shear the solid boosters away from the core stage. This structural failure automatically triggers explosive charges built into the rocket. In an instant, the vehicle and its payload are completely destroyed. The debris scatters over 12 square kilometers of mangrove swamp. Yet, investigators quickly realized that not a single mechanical component had actually failed. By mapping the official post-accident telemetry, investigators isolated the exact moment the system compromised itself. Looking closely at the accident track between 36.7 and 37 seconds, the internal navigation sensors report a malfunction, immediately followed by the excessive swiveling of the thrusters. The rocket's hardware performed perfectly. It tore itself apart because its internal software told it to. To steer a rocket through the atmosphere, the onboard computers need to know exactly where the vehicle is, but a rocket has no windows and it doesn't use GPS. Instead, it relies on an inertial reference system, or INS. The INS measures the physical forces acting on the rocket, its linear acceleration, and its angular velocity. By multiplying those forces over a strict interval of time, the computer continuously calculates its exact position in the air. The Ariane 5 was a massive upgrade over the older Ariane 4, designed to carry heavier payloads. To achieve this, it was built to produce a much higher initial acceleration right off the launch pad. This post-accident slide shows the result of the new design. Ariane 5's trajectory required a pronounced pitch, creating horizontal velocities 5 times faster than Ariane 4. Inside the computer, this extreme speed quickly saturated the capacity of the variable assigned to track it. The physical rocket was successfully flying a new, aggressive trajectory, but its internal logic was still expecting the slower, gentler flight profile of the older model. Inside the code, that horizontal velocity was captured as a 64-bit floating point number. The INS software attempted to convert that massive 64-bit value into a much smaller 16-bit integer. The system tried to cram the massive data volume of the new rocket speed into a digital container simply too small to hold it. Looking at page 5 of the inquiry board report, we see why this happened. To keep the computer's CPU workload under a strict 80% target, engineers deliberately chose to omit the software protections that would have caught this specific conversion error. When the 64-bit number exceeded the 16-bit limit, it triggered an operand error. In response to this unhandled exception, the active INS processor immediately shut itself down. The rocket had a backup INS running in parallel to prevent a total failure. But because it was running the exact same software and receiving the exact same physical data, it had already crashed 72 milliseconds earlier. With both navigation computers dead, the INS hardware transmitted a diagnostic failure pattern to the main computer. The main computer blindly interpreted that error code as extreme but perfectly legal physical flight data. Believing the rocket was violently off course, the main computer ordered the nozzles to fully deflect. A microscopic data overflow cascaded into a literal mechanical steering correction. The final detail of the software failure is the bitterest. The specific calculation that caused the overflow was a routine alignment calibration. This ESA malfunction slide notes that maintaining this alignment mode for the first 50 seconds of flight was an operational requirement for the older Ariane 4. For the Ariane 5, This calculation served absolutely zero purpose after the rocket left the launch pad. The software attempted to maintain a stationary alignment grid while moving at supersonic speeds. The resulting calculation was irrelevant to the mission and physically impossible for the processor to resolve. If this legacy code was both useless and fatal to the new rocket, why wasn't it caught during the months of system simulations? The engineering teams fell into a trap of assumption. Because the software had flown successfully on the Ariane 4, they believed it was proven and safe. They never connected the physical INS hardware to a simulator and fed it the actual high-speed flight trajectory data of the Ariane 5. The independent inquiry board tasked with unraveling the disaster had to examine how a culture of assumed reliability could destroy a flagship mission. The board's final report concluded that the failure resulted from a complete loss of guidance data due directly to specification and design errors. The extensive pre-flight reviews had simply failed to test the system against the real-world conditions it would face. The loss of the Ariane 5 demonstrated that physical hardware is entirely bound by the logic that controls it. Blindly copying legacy code without relentlessly testing it against the new physical reality it will operate within is a guaranteed recipe for failure.